and we leave the other half to next week. And we also talk about CDMA code division multiple access technology. And the last lecture on April the 8th, no, sorry, the 7th, yes. We'll cover the last topic, which is 3-generation networks, and a short review to prepare for the final exam. All right. So let me check the chat window and see any question before we start the lecture. Okay. Is there a quiz today? Okay, so today there's no quiz. But for next week, there will be a quiz. All right. So, and it will cover, for next week, it will cover multi-rate transmissions, basic operation of cellular networks, radio frequency technology and design, and the first part of the 2G networks. Okay, so next week there will be a quiz, and we should start preparing for the final exam. So, so please study for the quiz so that you can be prepared for the final exam, right? So again, next week there will be a quiz on multi-rate transmissions, basic operations of cellular networks, RF technology and design, and the first part of the 2G networks. Okay. Yes, exactly. Everything after the starting from multi-rate transmission until today. Everything starting from multi-rate transmissions until today. Okay. All right. Yeah, we should start studying to prepare for the final exam. All right, so let's continue the lecture on cellular networks. So just to summarize, in this course, mobile communications, we have covered two technologies at the beginning. One is wireless local area networks, AO 2.11 standards. And then the second technology is mobile ad hoc networks. So when we talk about wireless local area networks, we cover the architecture, the medium access control. And then when we talk about mobile ad hoc networks, we cover mostly on routing and transport protocol, which is modified TCP version for MANETs. So now we go into the third technology, which is cellular networks. So with wireless local area networks and with mobile ad hoc networks, they are contention-based medium access control. They're based on contention-based medium access control. That means everyone fights to get access to the channel or the medium. With cellular networks, medium access control is schedule-based. That means we use deterministic algorithms to determine who's going to use the medium next. And we've seen frequency division multiplexing. We've seen time division multiplexing. So those are the two most commonly used medium access controls schemes for early cellular networks. Now, with the most recent cellular networks, we use something called CDMA, code division multiple access, which is much more efficient and which can support high data rates. So we'll talk about this technology next week. So in terms of cellular networks, we're not going into too much math in this sense. We talk about the technology, the architecture, so that you are familiar with how cellular networks are operated. The only exception is the math part within the CDMA. It may involve a bit of math, and we'll see this next week. Otherwise, the material on cellular networks is lighter than the previous two types of networks, wireless LAN and mobile ad hoc networks. Okay. All right. So So let's continue with cellular networks. Let me open the slides here. Okay, so we'll talk about RF technology, and another common technology is sectorization. So we'll talk about that in the second part of this lecture. So a few definitions. Duplex, the first one is duplex. So duplex is a point-to-point system. So basically it's a connection between two entities that has two devices or two parties, and they can communicate with each other in both directions. Okay, so both directions can talk at the same time. So the telephone is one example of a duplex system. So half duplex means that each party can communicate with the other, but not simultaneously. And as an example of this is the walkie-talkie two-way radio. So I'm not sure if you have used a walkie-talkie before, but only one person can talk. The person would press the button on the walkie-talkie and then talk, and then releases the button. At that time, he or she cannot cannot send the message over the walkie-talkie anymore, right? And at that time, the other person can press a button on their walkie-talkie and talk to the other party, right? So that's half duplex. Another term is simplex. Simplex means that only one device can transmit, the other cannot, and the other person or the other party or device can only listen. An example of this is the broadcast radio or broadcast TV. You cannot talk back to the TV anchor. You cannot talk back to the TV host. Another is surveillance camera. Again, the same thing, or the baby monitors. So you can hear the baby can talk, can cry, and then you can hear the baby, but you cannot talk to the baby. So we can emulate or simulate full duplex communications using a half duplex communication link. Okay, in the sense that if you have two half duplex communication links, you can combine them. And let's say each link uses a different frequency. And in that sense, if you have two links, two different frequencies, then two parties at the two ends can talk to each other. You give one person, each person a half duplex link. So in that sense, they can talk in parallel simultaneously without any interference. And that's how we can simulate a full duplex link using two half duplex links. And the way to do this kind of emulation is to use time division multiplexing or frequency division multiplexing. All right, and we've seen this before, so I'm not going to spend much time on this in the sense that you must have learned this in 3213. So with time division multiplexing, we divide the medium into time slots, and each user would get one time slot in turn. So they would take turn in order to use the medium. So in cellular networks, the way it works is, so I think we should go back to the previous example. Sorry, 1 second. We could have two links. One is downlink and the other is uplink, as we've seen before. So in cellular networks, the way it works is they would assign a frequency to the downlink and a different frequency to the uplink. And within the downlink, the time is divided into time slots. Similarly, in the uplink, the time is divided into time slots, right? And of course, as the data rate increases, we will allocate more time slots to each link or to each frequencies. So time division multiplexing is good when the traffic in the uplink and downlink are symmetric, in the sense that we have similar rates in the uplink and downlink. So otherwise, if only one link is used heavily, but the other link is not used a lot, then we're wasting the frequency on the link that is not used heavily. So in this case, time division multiplexing is good only. It's good when we have symmetric uplink and downlink data rate. Right, sorry, 1 second. Sorry, it's good when we have a different data rate, because you can cut the frequency into more time slots and you have more users. With frequency division multiplexing, if you have symmetric traffic, then you can symmetric traffic. What it means is the traffic in the uplink and downlink are similar rates. Then you should use frequency division multiplexing. Otherwise, you would waste bandwidth. So with time division multiplexing, we have the flexibility of cutting the medium into as many or as few time slots as we want. So in that sense, if there's a asymmetric data rates in the uplink or downlink, we can accommodate that kind of asymmetry. Okay. So the example of, in real cellular networks, the UMTS, the 3G third generation networks uses TDD, time division duplexing. Similar for this as well. So I'll just list here as a sample of networks that uses TDD, right? But later you can, we go through all of this, okay? So there's a question here, even if uplink and downlink are in different time slots, we can still consider simultaneous communication. Exactly. So if the uplink and downlinks are in different time slot, we can still consider as simultaneous communication. When we say simultaneous here, that doesn't mean they have to talk at the same time. But what it means is the data can be carried in parallel, uplink and downlink, all right? Even though they're not in the same time slot, but because the time slot is very small, very small, very short. So the users will not detect the lag in receiving or sending. And in that sense, the user will feel as if the whole frequency, the whole uplink or downlink is reserved for them. So that's why they feel that they have simultaneous communication between the mobile phone and the base station. All right. So in this case, remember the time slot, they are very short. User would not detect the lag or the delay when waiting for other people to use the time slot. Okay. All right. So again, so with FDD, frequency division duplexing, of course, the transmitter and receiver operate at different frequencies in the sense that the uplink uses a different frequency and the downlink uses a different frequency. And within each frequency, we can have time division duplexing as well. So frequency division duplexing is more efficient when we have symmetric traffic. Otherwise, if we have asymmetric traffic, the whole frequency is not used very often, so we're wasting bandwidth there. Okay. So with compare with FDD, TDD could waste bandwidth during high handovers, because when the handover process is happening, those time slots will not be used. So basically, when a phone moves from, let's say, a station A to station B, both of them would have to allocate time slots to the mobile device. But the mobile device would use only one of the time slots allocated to it because it's moving from one place to another. So in that case, we're wasting part of the bandwidth, either at the old or the new station, depending on when the mobile device moves from one station to another. With the time division duplexing, the latency is higher, right? For the same reason I said before, each user is given a time slot. So a user has to wait until his or her time slot in order to communicate or to hand over. And it requires more complex implementation, more complex circuitry. Okay. So the example of a system that use frequency division duplexing FDD is CDMA 2000 UMTS, wideband CDMA, and WiMAX. WiMAX is dead. We don't use WiMAX anymore, but it's a system that used FDD. Okay. All right. So when we talk about FDD and TDD, the main idea to keep in mind here is a cellular system, a cellular network uses both FDD and TDD. So the frequency would be divided among different channels. And then within each channel, we can use TDD to divide that frequency to many users. Okay. So that's the main idea there. And by doing this, by combining FDD and TDD, we can simulate full duplex communication using half duplex links. Okay. Right. So cellular frequency bands. Now, so you will see a lot of diagrams. We will see later, right? So let's start with. So these are the most common frequency bands used in cellular networks. The 850 megahertz band, 1900, 700, and 2100 bands. Now, why do we have these numbers? So let's consider the 850 megahertz band. Okay, so the name comes from the lowest frequency and the highest frequency. So in this band, the lowest frequency is 824 megahertz, and the highest is 894 megahertz. So we use a frequency that is somewhere around the middle of this. That's easy to remember. So that's why we use 850, right? Of course, we could choose, we would do the exact calculation. So let me say if we take A24 plus A94 and divide it by 2. If we do the exact calculation, then the middle frequency is around 860, right? But 860, if you take A24 plus A94 and divide it by 2 to get the exact middle frequency, that would be around 860. 860, right? So, but 860 is not easy to remember. So that's why they use 850, okay, 850. So basically the 850 is the middle frequency of 824 and 894, somewhere in the middle. It's not exactly in the middle, but somewhere in the middle, okay? So because people may wonder, where do we get this 850, all right? All right, so this spectrum, a long time ago, before the 1980s, it was given to the TV industry to broadcast TV signals. So in the old days, we don't have cables, right? We don't have internet TV. So though in those days, TV station would broadcast a signal in the air wirelessly, and then each TV set would have a set of antennas, and then we people adjusted the antenna in order to get the best reception of the signal. So back the old days, this band is given to the TV industry, but they even did not use this spectrum either. So around the 1980, the FCC, basically the Federal Communication Commission of the US, they took back this band and they gave this band to wireless service provider to use for cellular networks. Okay, all right. So next, so and again, the number 850, it comes just the middle of this frequency band, and it's a number easy to remember. Right, so the benefits of the 850 megahertz frequency is the short wavelength. It has a short wavelength, and because it has a short wavelength, it can travel farther than because it's at low frequency, it can travel farther than the other wavelength. We'll see later. It tends to be line of sight, right? So and it can be easily reflected off buildings, cars, or trucks. So you would have better signal reflected instead of being absorbed by a building. And if being absorbed by a building, then the signal will become very weak, right? So that's why it's reflected. So it's better in that sense. And it can be easily absorbed by foliage like trees or forest. And this can be good or bad. It's good in the sense that it's good for frequency reuse. All right. So because with frequency reuse, we can have, if absorbed by tree, so that means the next cell would have less interference. So that's good in that sense. If the signal going through a forest is absorbed by trees, then in the next cell, the signal will become weaker. So there would be no interference in the next cell. On the other hand, it's bad because it's absorbed by trees, so the signal becomes weaker. All right, so so that's why we have signal attenuation. So this can be a good or bad property. All right. Oh yeah, sorry, right. So this one is better. This have short signal wavelength compared with the other. When we say short here, we compare with other frequency, and this to answer Shadan's question. Compare with other frequency that we'll see later. Okay. Let's say if we compare it with the 700 megahertz spectrum, okay, or we compare with lower frequency spectrum, okay, lower frequency spectrum. Okay, so because this one is the first spectrum that was taken back from the TV industry and given to cellular networks, cellular service provider. Okay. All right, so now we go to the next wavelength. Now, again, I don't expect you to remember the detail of the bands here and the frequency. You just need to remember the megahertz band, all right, because these are the common frequency bands used by cellular service provider. All right, so now the 1900 megahertz band. So these band again this band was given by the FCC to the PCS carriers in the early 90s. So PCS stands for Personal Communication Service. Okay, and that's why it's also called the PCS band. So basically, it's the first band officially given to mobile service. So it's called the PCS band for that reason. And if we compare this old spectrum with the new spectrum, so this old spectrum is better. It can go to hard to reach places, again, because of lower frequency. As we said before, lower frequency, we can go further. And it can penetrate hard to reach places better than high frequencies, right? And then again, the new 700 megahertz spectrum will be even better than the 850 megahertz spectrum with respect to the distant travel and the hard to reach places. Okay, so and again, this is the illustration of the 900 megahertz band. So it is even cut further into smaller bands. And each band is given to a carrier, right? Each band, let's say A. So if you have A and A prime here. That means both of these would be given to a carrier. And let's say A will be the uplink and A prime is the downlink, or the other way around, right? Again, for D and D prime, D will be given to uplink, D prime given to downlink, for example, or the other way around. And you can see that we do this, the uplink and the downlink, they are far apart from each other, right? This is 1850 and this is 1930. So that we have the separation of frequencies. So when you have an uplink and downlink and you have a large separation of frequencies, the uplink and downlink can operate in parallel. As we said before, we have a full duplex by using two half duplex. So A and A prime are the half duplex channels, and they work in parallel, uplink and downlink. And because of the separation of frequencies from 1850 and this is 1930, there would be no interference among them, right? Now, of course, you would not allocate, let's say, A and D, right, as downlink and uplink because they are close to each other. Then there may be interference between them if you use them as uplink and downlink for the same mobile phone and base station, all right? So that's why when you see A and then A prime, A indicates one link, the other is the, let's say, the uplink, and the other is the downlink, all right? Yeah, the same for B, D, B, E, F, and C. All right, so this is the 1800 megahertz band. The 700 megahertz band. So again, a part of this band again was owned by television and broadcaster, radio or TV broadcaster. But again, they didn't use this band a lot. So in 2009, this band was returned to the government. And then the government would sold these bands, cut into many other bands, smaller bands, and then sold them to wireless carrier provide service, cellular service provider. And because this is a very low frequency, so they can travel further and they can penetrate walls, obstacles. So that's why it is very suitable, very good for broadband communication in general and for public safety uses, right? Because you want any public safety announcement to reach everyone. And because of the low frequency band, so higher distance it can travel and the ability to penetrate walls. This band is very suitable for public safety uses. And then the carriers who bought the licenses for this band will use them for the 4G and LTE deployment. So currently the 4G networks now. Okay. All right. So so the 700 megahertz band is divided into two smaller bands. One is about 48 megahertz and the other 60 megahertz. And just this is just a rough number of how much it costs to build a nationwide wireless network. For the 700 megahertz spectrum, the cost is about 2 billion. And the 1900 megahertz band, the cost is about 4 billion. And the reason for this is because this is at a lower frequency, so it can travel further. So that means you don't need as many base stations, and it can travel, it can reach hard to reach places. So again, you don't need any other special equipment for those places. So that's why the cost is lower. Okay, and in general, the costs are lower in rural areas because of less interference and wide open spaces. And again, the cost lower for this 700 megahertz because, as we said before, it can broadcast as cover twice as many square miles, again, because of lower frequency. So the distance it can cover will be larger, as we said before. Yeah. All right. I've heard that then I use 600 megahertz for 5G services. Is that right? Yes. I mean, so now these frequencies are becoming very, very expensive, because as more subscribers join the market, you need to provide more services. So now they use even lower frequency as much as they can get from unused frequencies to support new services. Exactly, yes. Right. Okay, so all right, so that is the 700 megahertz band. And this is just some tidbit about the 700 megahertz spectrum. So it was divided into 5 blocks, and in 2008 they held an auction to sell these. So the government, the U.S. government, they held an auction to sell these 5 blocks, and in total they received about 19.5 billions. And then because of this spectrum, Verizon and AT&T together accounted for about 16 billion in total revenue. They bought most of these bandwidths, so they accounted for about 16.3 billion among these 19.6 million raised in the auction. Okay. Right. So, and again, this is an illustration of how the 700 megahertz spectrum was divided. So again, you can see that we have A and A here. Basically, it stands for the uplink and downlink of 1.4 duplex frequency band, right? B and B here, uplink and downlink, and C here. Okay. So again, I don't expect you to remember these numbers, but to let you know that this is how it's divided into blocks A, B, C, D, and E. Okay, and again, the number 700 is an approximate between 698 megahertz and 746 megahertz. Okay. Right. So, and then there's another band, which is 2100 megahertz band. Okay. It's also called AWS, Advanced Wireless Service. So this band is used for mobile voice and data services, video and messaging. And it's used in the United States and Canada. So this band was again auctioned in the US in 2006. And this is the division of this band into several other smaller bands. So you can see that the first half of this band here is for the uplink from the mobile to the base station. So mobile here means to send from the mobile to the base station. And the second half here is for the downlink from the base station to the mobile phones. Again, the uplink, the first part is AA, BB, and CC, and so on, right? And again, the number 2100 is an approximate middle of 1710 and 2155. All right, so that is easy to remember. Okay, it's not the exact middle of this frequency band, but it's a number that's easy to remember. Okay, all right. So in summary, we have 4 frequency bands, at least from this textbook. I'm pretty sure that there are more frequency bands now after the textbook was published. 850, 1900, 700, and 2100 megahertz. Okay, and just as a note about this, the frequencies are very expensive resources, so that's why we have some kind of auction, and whoever is willing to pay more will get that frequencies, especially with the explosion of cellular services these days. Okay. All right, so so another topic another point about technology we should keep in mind is about the obstacle caused by large office buildings. So they usually have a metallic coating. So this is good for the environment in the sense that it reduces the heat or the cold, to protect the building from heat or cold. So it's good in terms of environmental concerns. But in terms of cellular services, it's not good because it will block the signal from outside to get into the building, right? To get into the building. It's harder for the signal to penetrate metallic coating. So the solution here is to use a microcell in the building. So basically, there is a microcell inside the building. And then there's a wide connection between the base station and the microcell. So now, instead of a mobile station inside the building communicate directly with a base station, now the mobile set, the phone, the cell phone, communicates with the microcell, and the microcell communicates with the base station outside using a wire or cable. All right, so the microcell can serve as a relay, right? Relay the signal from the mobile phones inside the building with a base station outside the building. Okay, all right. Okay, so another, so today, I mean, these days, in the past, we talk about frequency reuse where we have cells, and then we would have 7 channels, and those 7 channels would be reused over and over the whole network. Now, these days, we have something called automatic frequency planning tools, and these tools will help the network administrator to allocate channels to base stations, so that to minimize the interference between cells and minimize interference within a cell as well, right? And these tools will help automate the allocation of frequency and channel assignment to the base station in a network. So in the past, these things had to be done manually using the frequency reuse, and the engineers would sit down with a map and try to figure out how to allocate the frequency in an optimal way to different base stations in the network. Now they have software to automate this process. Right, and so this is something we've seen before. It's called pair channel. So we have a downlink from the base station to the mobile phone and uplink from the mobile phone to the base station. Okay, and the downlink is called the forward channel, and the uplink is called the reverse channel. Okay, right. So so this is just a repeat of what we've seen before. So on wireless transmission in a cellular network require a paired channel to function. When we say a paired channel, that means this, a downlink and uplink. All right, a downlink and an uplink. All right, and so the forward channel is the downlink, and the reverse is the uplink. So when the two channels use different frequencies, so we call this frequency division duplexing. We've seen this before. And when the 2 channels use the same frequency, they can use the same frequency. It's known as time division duplexing. So that means if we have 2 different channels and we allocate to them, so that's good. We have, each will have different frequencies. But if we have only one frequency to allocate to them, then of course we have to divide the medium into time slots, right? So that when the base station send, the mobile phone should not send. So they just have to take turn in order to use the medium. So in that case, we call it time division duplexing. Okay. All right, and something called, and there's a concept called channel spacing. So channel spacing refers to the amount of radio spectrum that allocate to every cellular transmission, as we've seen before. Okay, and then there's something called the control channels. Okay, so in addition to the channels that used to transmit data, there's something called a control channel. It's also called a pilot channel. And each cell base station in a wireless system should have at least one control channel assigned to it. And in sectorized base station, each sector will have its own control channel. So we'll talk about sectorized base station later. So when a mobile phone press when the user of mobile phone presses the send button to place a call, the phone first will scan the environment and select the strongest control channel signal in its assigned frequency band, right? Because a phone may be connected to more than one station. And in that case, it may be close to more than one base station. And in that case, it will scan the environment to get the strongest signal, stronger channel, control channel, and then it will associate itself with that base station. Okay, right. So before we go into the administration tasks of the control channel, we can take a quick look at the example of the control channel. Okay, so if we take a quick look at this example, so this is the standard IS-95 forward channel. So this is a very old standard. It's in the second generation network. Okay, and this is the forward channel, which is the downlink, right? This is a downlink. So this is the forward CDMA channel at 1.23 megahertz. And this is the carrier bandwidth transmitted by the base station, right? This is the downlink. So that means the transmitter is the base station. So we can see here the pilot, right? The first block here. The first block here is the control channel. Okay. And basically this frequency is divided into smaller frequencies into, let's say, some different channels. So channel number 0 is used for the control purposes. So this is the pilot channel or control channel. And then it has other kind of channel as well, like synchronization, for paging, etc. Now, so these are also for other administration tasks, okay? But the data is carried in the traffic channels here. So channel 8, 9, 10, and so on, up till 31. 32 is used for synchronization, and then 33 and 63. So basically, these are the channels reserved for data for traffic. And within a traffic here, it's divided into two smaller channels. Sub-channels. One is for the data itself, right? It's for the voice or message from a base station to a mobile phone, for example. And then the other sub-channel is for power control, all right? Mobile station power control sub-channel. So power control means that when a mobile station is close to a base station, it can reduce its transmission power, right? So for two reasons. So that the first reason is it would not overwhelm the signals from the mobile stations that are located far away from the base station. And the second purpose is to save energy consumption, right? Because you want to minimize the energy consumption by minimizing the power, transmission power. So that's why there's a power control function on a mobile phone in order to save energy and again to make sure that the interference is minimum in that cell. Okay, so the traffic channel here is further divided into two sub-channels. One is used for the data itself, and the other one is to tell the mobile station either to reduce or to increase the transmission power depending on the distance and depending on the channel quality. Okay, right. So so these are the tasks of control channels. So basically this channel here, pilot, it will carry the signal or carry messages to do these tasks. So it sets up wireless calls, locating or paging mobile phones, collecting call information, collecting traffic data from base stations, allows support mobile registration, autonomous mobile registration, and initiating or assisting in call handoffs, call handoffs mean when a mobile station moves from one base station to another. All right, so these are the tasks of a control channel, right? Okay. So the frequencies of control channels will be different for each wireless carrier in every market. And then the, so let's say, and then they have different frequency for this, okay? All right. All right, so now we'll talk about another concept, which is called sectorization, okay? So in the past, when cellular networks first appeared in the market, when the number of subscribers increased, the service provider had to split cells so that they can put more base stations, so that they can serve more subscribers. So this is one example. So assume that the service provider now had to sell base station here, right? Now, if they have an increased number of subscribers, they had to create more base station because each base station can support only a limited number of subscribers. So in this case, they created one more base station. So now they can increase the coverage by 33%. That means they can support 33% more subscribers, okay? Now, but this is expensive. So you can imagine if you have two base stations here. Now to do this, you have to move these two base stations, right? You have to dig another place to move these two base stations and that one more here. So this process is very expensive. And every time we want to move base station, we want to add new base station, service providers had to go through a process necessary to develop a way to increase the system capacity without having constantly splitting cells, because it's very costly. So the way to do this is to use sectorization. And the service providers sectorize base station in order to obtain more capacity from each base station in the deployment. Okay. All right, so what does that mean by sectorization? So, so this is the example. So in this case, we have something we call omnidirectional base station. That means the base station covers 360 degrees around it. All right, so we have one base station in the middle, and it covers 360 degrees around it. This is called omnidirectional base station. Now, so now instead of having one base station, we can have three, right? But now if you have three, they cannot be omnidirectional because they would interfere with each other. Instead, each station is given 120 degrees to cover. So now we divide 360 degrees into three sections, and each station would get 120 degrees of space. So that each would cover 120 degrees of space. And this is called sectorization. It's basically so if we use 6 antennas, then each of them would cover 60 degrees, right? Okay. And each sector is viewed as a new cell, with its own set of frequencies and channels. And again, this chain happened at the same location, all right? So you see it happened at the same location, then you don't need permit in order to dig a new place or to move the base station. You can just add more antenna, and you add 3, it will cover 3 directions, 6 directions, all right? And each of these sector will be considered as a new cell. So if someone, if a user is currently in this sector, if the user moves to this sector here, right? So in the past, this user still stay within this cell, but now with the new configuration, this person will perform a handover or handoff, and then hand over to this base station. The same thing, if it moves to this location, there will be a handoff and handover to this base station. All right. So this way, we can increase the number of subscribers by almost 3 times, right? So now you have 3 separate, different cells. Okay. All right. So with sectorization, we can reduce the interference among the co-channel cells. We can support more frequency reuse, right? You can support more frequency reuse because now they do not interfere with each other. Let's say from this part and this part. The range of this sector is a bit larger than the omnidirectional cell. So that means now this circle here is a bit larger than this own circle, right? If we measure from this to the distance here, it can be go a bit further. Okay. And then all the antennas for each sector, they are all located at the same base station, and they are called a subcell. Okay, and they are housed in the same base station. So because of this, it's much cheaper to increase the capacity, right? Sectorization is to increase the capacity, not the range. Right, exactly, not the range. The purpose is to increase the capacity. The purpose not to increase the range, right? But as a side benefit, the range can be increased a bit, right? Because now imagine with one base station, you have to cover 360 degrees, right? With one base station now, we cover only 120 degrees. So that means we can with the same transmission power, we can reach a bit further, all right? So the purpose of this is to increase the capacity, but one side benefit is the range can be extended a bit further, okay? Because of the concentrated transmission range. Okay. Yeah, so the range of a sector is a bit larger than in the omnidirectional cell. Because of that, okay, so again, the objective is to increase the coverage. And by that, we can increase the capacity of the network to support more subscribers, right? We can have 120 degree sector, 90 degree or 60 degree sector, depending on how many antennas we are willing to pay to sectorize the cell. Okay, so this is one example here. So in the past, in this network, there are 1, 2, 3, 4, 5, 6, right? With 6 base stations. Now, if each base station is sectorized into 3 sectors, so now we can have 6 times 3, now 18. So we can have 18, basically 18 subcells, right? So we can support 3 times more subscriber using this network, okay? All right, so sectorization helps, as we said before, minimize or helps to eliminate co-channel interference. It can help optimize the frequency reuse plan, and it increases capacity of a coverage area, okay? And again, each sector has its own assignment of frequencies, radio channels, and control channel. Basically, each sector is its own cell, considered as its own cell. Okay, so this part this lecture is from chapters 4 and 5 in the textbook, Cellular Network Design Operations. Okay. All right, so now we take a break for 10 minutes, and then we'll be back at 3:40, and we continue with the second generation cellular networks. Okay, so we'll be back at 3:40. Okay, so. So there's no quiz today, but next week there will be a quiz on multi-rate transmission up to today's lecture. Yes, next week the quiz will start from multi-rate transmission up to today's lecture. Okay. Okay, so we'll take a 10 minutes break. All right, so let's get back to the lecture. Okay, so before the break, Shadan mentioned the 600 megahertz band. So in 2017, in the US, the FCC auctioned that band. So I didn't know that the Canadian government also auctioned that band in 2019. So now, yeah, so now the Canadian cellular networks service provider also uses the 600 megahertz band. And of course, they would use it for the latest generation, which is 5G for sure. They keep they still using the previous bands for older generations. Okay, so now we'll go back to cellular networks. So in this lecture, we'll first start with a overview of the cellular network generations. And we'll talk about development and history of cellular digital cellular technology. We talk about the advantages of digital wireless technology over analog systems. And we go into detail of the second generation system, which is global system for mobile communications. One second, let me open chat here. Okay. Okay. So so the cellular network generation overview. So in the past, so now we have 5G as well, but in the textbook, they cover up only until 4G. So we have 1G, and then we'll go through each generation later. And then from 2G, we have other evolution, improvement. We get 2.5, 2.75G. And then 3G and 3.5 and 3.75G, 4G, and then 5G. Okay, so so this is a quick illustration of different cellular network generations. So the first generation is all analog, right? There's no digital, and it's based on the frequency division multiple access. Okay, so it's on analog. And then in the second generation, we moved to digital wireless technology, and we use time division multiple access. So basically, it's a combination of FDD and TDD, not just TDMA, right? Because we have to divide the frequencies into different bands in order to maximize the usage of the frequencies. So it's a combination of frequency FDD and TDD, time division duplexing and frequency division duplexing. And the most popular system is GSM, Global System of Mobile Communications. The IS-136 is in the US, and this is the standard developed by Europeans. This is in the US. And then from this, we have another evolution, which is IS-95, and this uses CDMA. From CDMA, we have CDMA 2000, and this is third generation. From both of GSM and IS-136, they evolved into a better version called Edge. And this is evolution data based on GSM, right? G stands for GSM here, GSM based evolution data. And it's also based on TDMA, basically both FDD and TDD. Right? And from IS-136, we have DO. DO stands for data optimized, and it's used both TDMA and CDMA. So this is 2.5, generation 2.5. And from here, again, it evolved into the third generation, UMTS, Universal Mobile Telephone Service, and it's used as CDMA. Okay, so next week we'll learn what CDMA is. Second. And then we combine so UMTS and the data optimized again, they evolved into LTE, long-term evolution, and this is 4G. And it used orthogonal frequency division multiplexing. This is another technology. So unfortunately, we don't have time to go to 4G. I think we have time only to go to 3G. Of course, if you want to know more about 4G in the textbook, there's a chapter on that part on 4G, right? But we only have time to cover up to 3G, third generation only. Okay. So this table summarizes all the details of different generation from 1G, 2G, 2.5, 2.75, up to 3, 3.5, 3.75, and 4G. So we'll cover everything from 1G to up to 3.75G, but not 4G. Okay. But again, in the textbook, there's a chapter on 4G. Okay, so let's go with the 1G networks very quickly. It's on analog, and then we go into 2G networks in more detail later. So 1G networks was launched in early 80s. And again, it's only for voice. It's only for voice communication. No data at that time. Everything is analog. And it used the frequency reuse concept. So this is the frequency reuse concept that we talked about before. So in this case, we have 7 frequencies or 7 frequency bands, and we reused these 7 bands throughout the network by separating, let's say, the cell that used frequency band 1 to separate them as far as possible. Similarly, for 4, separate them as far as possible, 7, by reusing these 7 frequencies and place them far away as possible to avoid interference. We can use the same set of frequencies throughout the whole network. Okay. And the popular 1G networks are AMPS. So this is in the US, Advanced Mobile Phone System. And then in Europe, we have Nordic mobile telephone. And then we have the European Total Access Communication System, and then we have Japan Total Access Communication System. So what we can conclude from this is that at that time, there was no standard whatsoever. So everyone created their own system, created their own services. There was no standard. And then around early to mid 1990s, digital services were introduced into cellular networks, and this is the first own digital cellular system. It also supports the mobile assisted handoff capability. And the prominent 2G networks are GSM. So this one was proposed in Europe. So this is a European standard. And then CDMA1, IS95A and B, or this is another name for this one. And IS stands for interim standard. Interim standard. That means there's no standard at that time, so they create their own. They call it interim standard until they created a permanent standard for everyone. And then the previous 1G network, AMPS, was improved into digital AMPS, and another name for it is IS136. So this is the network, and then they try to standardize it, so they call it IS136, and this IS195 for CDMA1. So this is in Europe, but later some American service provider also use GSM, and this is an evolution from the previous analog service, AMPS, and of course, so this is in the US. And then after this, there were more improvements, more enhancements, evolution added to the previous 2G network. So they have something called 2.5G, which includes GPRS. We'll see these later. and then the CDMA 2000 technology. And they can support data rate up to 144 kilobits per second. Now, compared with these days, this is very low, right? But at that time, it was considered as high speed. And then some more improvements were added to 2.5G. So we have something called GSM-based edge wireless data technology, and it's sometimes labeled as 2.9G. So basically, it's not good enough to consider 3G, but it's much better than 2G. So they call it 2.9G. All right. And then after that, 3G networks. So 3G network can have much higher data rate than this, basically almost 3 times. So 384 kilobits per second or higher. And the most prominent 3G network is UMTS, Universal Mobile Telecommunication Service. So in the US, UMTS and CDMA 2000 were used in 3G networks. And then in these networks, in 3G networks, both FDD and TDD were used. And FDD means that different frequencies are used, and TDD means that one frequency is used in both uplink and downlinks, as we've seen before. Okay. So more enhancements were added to 3G networks. So we have HSPA, high-speed packet access, and this is an evolution from UMTS. And then HSPA was enhanced with even more features, more technology. We have HSPA Plus, and this is on 3.75G networks. And so 4G networks consisted of WiMAX and long-term evolution. So WiMAX never really picked up, and it's considered dead now. So now the true 4G technology is called LTE Advanced, right? So these days our service provider, let's say I'm with Roger, and they use LTE or LTE Advanced, all right? So when I turn on my phone, I see the term LTE there. So basically now we are in the 4G networks. All right, so all of this is a summary from section 8.1 in the textbook. If you want to know more about different generations of wireless cellular networks. So now we're talking about the GSM, the Global System for Mobile Communications. All right. All right, so just before we go into this, just as a side note that the 2G technologies no longer exist in most wireless networks, because by around 2016, so basically when the book published was in 2014. So the plan was in 2016, most wireless carrier would sunset the 2G technologies, okay? So just as a side note, so GSM and TDMA may still be operational within some networks to accommodate older mobile phones up to some point. But obviously, it's not the first choice technology to carry traffic. Now that we have much better technologies, right? But it could be kept around for regulatory or operational reasons. All right. So again, as for some historical context, the performance of cellular networks is really restricted by co-channel interference, meaning that different mobile phones communicating with the base station within a cell would interfere with each other. And then up until around mid-90s, cellular service provider only use the analog technology and the 850 megahertz spectrum in the network, as we've seen before. And during that time, in the first generation, frequency division multi-access was the method used to get more capacity, right? And as we said before, in order to increase capacity, usually they use cell splitting. That means adding more base station. Of course, this is not the best solution. It's expensive as well. It was expensive as well. So in the early 90s, the first digital wireless technology in the US was created, and it's known as IS-54, and IS stands for interim standard. Again, it's an enhancement from the previous AMPS. AMPS was analog, so now they add some digital aspect. They call it DAMPS, and it used TDMA to increase the system capacity. Okay, so and this slide will list 3 types of digital technology that were used around the world in the early to mid 90s. So in the US, we have IS-136 that used TDMA, and it evolved from IS-54, the AMPS. And then we have also, at that time, we also had GSM. It's a global system for mobile communication. And it also incorporated CDMA into the network. So at that point, CDMA was a new technology at that time. So IS-136, of course, is now a dead technology. GSM, on the other hand, evolved over the years into more advanced technologies such as UMTS and SSPA. Right? So this is the third generation. This is 3.5G networks. And then the CDMA technology also evolved into more advanced digital wireless technologies as well. Right, so now, of course, so now we compare the advantages of digital wireless system compared with analog cellular system. So of course, a digital system can support, it can have more capacity than analog system. So that's the first thing, higher capacity. It costs less than analog system, all right. It can produce cleaner and quieter signals. It provides greater security. CDMA is not easy to hack. With, let's say, frequency or time division multiplexing, you can have something called overhearing, right? Or it's called overhearing. So that means they can eavesdrop some conversation if we use frequency or time division multiplexing. With CDMA, it's much harder to hack. So again, we talk about CDMA next week. So with 2G phones, there would be no cloning fraud. While in the past with analog signal, the hackers can access the AMPS control channel transmission in order to hack into the system. The mobile phones are smaller and more lightweight compared with analog phones. And then with digital technology, the mobile phones can play a role in determining whether call handoff is needed, and to what cell it can hand over. So it helps to reduce the probability of dropped calls during the handoff process. So that means the system, the call handover process is more robust, more reliable. And with digital technology, we can use bit error rate, we can use frame error rate to determine channel quality in order to assess interference instead of using decibel. So with decibel, we have to use, with analog system, we have to use decibel, the signal strength, instead of using bit error rate or frame error rate. All right, so those are the advantages of digital wireless compared with analog system. So now we go into the GSM technology, okay? All right. So first, GSM technology is a TDMA technology. So again, when we say it's a TDMA technology, that doesn't mean it uses only TDMA. The system uses both FDMA, frequency division multiple access, and TDMA as well. So that means the network is divided into different frequencies. And then in each frequencies, TDMA is used in order to allocate a time slot to each users. Okay. And we have separate channels for uplink and downlink, as we've seen earlier, right? So we use FDMA here so that we can allocate separate channels for the uplink and for the downlink. All right, so this is a bit of the history of GSM. So as we've seen earlier in the 1G networks, the US had its own system. Europe has its own system. The Nordic countries has its own system. Japan had its own system. So basically, even in Europe, there were 6 cellular systems that were incompatible to each other. And because of that, a mobile phone designed for one system could not be used with another system. All right, so, and forget about moving from one network to another, handover, right? So for now, if you have service with Roger, when you travel to another city or province, you can go into a network with Bell or with Telus without any problem. But in the past, before GSM was developed, even in Europe, there were 6 cellular systems, and a mobile phone designed for one system could not work with another system. And as I said, forget about roaming, just forget about roaming. So that's why at that time there was a group. It's called Groupe Spécial Mobile. So this is in French. It stands for Special Mobile Group. Right? And they were working to develop a digital cellular standard for the European market. So the GSM first stand for the name of the group, but later as the standard was developed, they changed it to Global System for Mobile Communication. So now that stands for GSM stands for this, and not the original name of the group that developed the standard. Okay. All right. So the first system was activated in around 1991, and commercial service began in 1992. And by 1996, there were more than 35 million customers in over 200 networks. And GSM has been deployed in the 900, 1800, and 1900 megahertz frequency bands. Okay, so that's why we went through those frequency bands at the beginning just to get an idea of what they are. Okay, and many of the American public, so PCS and for Public Personal Communication Service. So many of the American PCS carriers again chose GSM as the standard in around late 1995. And the system works by using TDMA, right? Time division multiple access. So basically, the system is divided into 200 kilohertz channels. Sorry, 1 second, please. So the network was divided into 200 kilohertz channel or carriers, and then each channel occupies 25 kilohertz, right? So if you take 25 multiplied by 8, right? So yeah, 25 multiplied by 8, you get 200 kilohertz, right? That's true. And then each of these channels can support 8 calls simultaneously, right? It can support 8 calls using time division multiplexing. Okay, so you can see this is how it works here. So each each channel like this 200 kilohertz, it divide into smaller sub-channels of 25 kilohertz. And then it will be divided into 8 time slots, and each user is given a time slot. All right. So now keep in mind that each of these time slots is very short. So even though a user is given only 1 time slot, the person could not perceive the delay while waiting for the other user to use the other 7 time slots, okay, because they were very, very short. Okay. All right, and the system uses something called vocoder. A vocoder is the shorthand for voice codec, right? A codec is a coder and decoder. So this is a codec used for voice, and it allows a user to use the 200 kilohertz channel, right? So each channel can transport 8 calls simultaneously. Basically, each user is given 1 time slot on this channel, and we have 1 channel for downlink and 1 for uplink. And again, each is divided into 8 time slots using TDMA. Okay. All right. So now we're talking about the architecture of GSM. Okay. So multiple 200 kilohertz channel will be assigned to each base station. And then among the 8 time slots we talked about earlier, 1 time slot must be allocated for control channel purposes. So that means up to 7 subscribers can use a 200 kilohertz channel simultaneously, okay? Because 1 is reserved for control channel, so the other 7 can be used for subscriber. And remember, we had a diagram before where we have the first block, the first channel is called pilot, that is the control channel, and the rest is for subscribers. Okay. All right, so this is the architecture of a GSM network. So a GSM network is divided into 4 subsystems. The first is called the base station subsystem. The second is called BSS. The second is called network subsystem, or NSS. And then operation and support system, or OSS. And the last one is mobile station subsystem. Okay. All right. So this is the diagram. So yes, I'll make it a bit bigger. All right, so this is a diagram of a network. Okay, so let me go back to this. All right, so the first subsystem is base station subsystem, which is BSS. So this is the block in which the BSS is illustrated. This block here, right? And then the second component is the network subsystem. So basically, this is the network subsystem. Okay, this part. And then the other one is the operation and support subsystem, OSS. So this is the OSS. Okay, all right. And then the mobile station subsystem is basically a mobile phone like this. Okay, so each of these mobile phone is called a mobile station subsystem, but it's basically a mobile phone like this. Okay, all right. So so let's talk about the base station subsystem first. So the base station subsystem would have let's say 3 main components, right? But we can see only 2 components in the diagram, because the third component is called the air interface. All right. So I would imagine the air interface is the air around the base station here. Okay, so that's called the air interface. But physically, that we can see physically is the base station controller, and the base station controller and the base station base transceiver station. Okay, So let's talk about the base station controller first. Let's see. So first, the base transceiver station. The base transceiver station is basically the base station. Okay, it's a base station, and it has a transceiver, a transmitter, and a receiver. So you can imagine this as the base station we've seen earlier. Or it could be a base station, let's say, with 3 directional antennas, with 3 sectors, or 6 directional antennas with 6 sectors, for example. All right. So a base transceiver station is basically a base station here, and it has a transceiver, a transmitter, and a receiver. Okay, and it communicates with the mobile phone here. And then the next component is from the base station subsystem. The other component is the base station controller. Okay, so base station controller. So the base station controller is the control computer that manages the base stations. All right. So if you consider the BSS here as a computer, then you can imagine the base station as, let's say, input and output devices, right? Input output devices. And if this is a computer, and if this were a computer, then the base station controller would be the processor and the memory, where it manages these input and output devices, right? And the BSC, the base station controller, they are usually housed at the MTSO location, the switching service, the switching office location. Okay, so if we recall, let me open the first lecture. 1 second, I'll open the first lecture with the diagram of the okay, so we stop share this one here, and then I'll share the second screen. Okay, so if we recall, sorry, this diagram we had before of the components of cellular networks. So this is a very simplified diagram, right? We have a bunch of base station, and then we have the mobile telephone switching office, MTSO, right, and the core network. So this basically is a physical location. It's an office, it's a building, right? And inside this building, equipment will be stored there, all right? So the base station controllers are housed in this building, right? In this building here, the number 4 here, all right, in this building. Okay, so I'll stop share this and we go back to this slide. Okay, so wait 1 second. All right, so if you consider the BSS as a computer, then the base station could be considered as input-output devices, and the BSC considered as the processor and the memory that control these devices. So the BSC are usually housed in the switching office building. They decide which radio channels are being used by which base station. They allocate the radio channel to base station in order to minimize interference among them or within a network. They manage the call handoff process between base stations. So when a mobile phone moves on one base station to another, these controller would manage that process for the handoff between base station. And they regulate or they control the transmission powers level of the base station and the mobile handphones, right? So again, in cellular networks, there's a function called power control. And the power control function, as I mentioned before, has 2 main purposes. One is to minimize interference, and the second is to save energy in the cell phone. So these are the the functions of the base station controller. Okay. All right. And then as a phone gets closer to the tower, the controller will tell the mobile phone to lower the transmission power level. And as the mobile phone moves farther from a tower or base station, the controller will tell the mobile phone to increase the transmission power, right? As we said before, it moves closer, reduce transmission power, further away, increases transmission power to minimize interference and to save energy, right? And then the base station controller also handle the overheads associated with the frequency management, the call setup, and the call handoff, right? So basically, in general, in summary, the controller manages the operations of the base stations here, and the operation of the mobile phones, right? Such as which radio channel to use, how to do handoff, how to do power control, right? So every function related to the base station, the towers, and the mobile phones. Okay. All right. So that's the first part. Now, let's see. So now we're talking about. One second. Let's talk about the OSS first, right? Because it's short. It's only one slide. The OSS is called the Operations and Support Subsystem, and it is the command center that is used to monitor and control the GSM network. Basically, it controls the whole network. All right, it controls the whole network. So, and if there's a outage occurs at the base station, the OSS can determine where that base station is located and what type of failure happened and what equipment the site engineer will need to repair the failure. All right. So basically, the OSS, you can consider this as the brain of the whole network. All right. The brain of the whole network. The BSC is just to control the base station and the mobile phone with respect to the call handoff process, power control, and the radio channel to use. But the OSS is the brain of the whole network. Okay, so that's the purpose of the OSS. So it's control the base station controller. It's control the network subsystem. Okay, right. So okay, so now we go into the network subsystem. So basically, the network subsystem is this block here. All right, the network subsystem is this block here. Okay. So this is the central component of the network, right? This is a central component of the network, and it has many components. Okay. So we go through the components. So this is the controller. All right. So this is the controller here. This is a controller, and this controller will control. This is the switching center. It will control. This is a switching center. It controls all of these components. All right. The first one is HLR. So HLR is a home location register. Okay, home location register. And the HLR is a database that registers user in a cellular network. Okay, so it's called home location registers. It registers users in the home in a cellular networks. And then we have something called VLR. So VLR stands for the visitor location register. So basically, when a user outside this network moves into this network to use the system, when we call it roaming. So this database will store information of that visitor. Okay, HLR is for user of the network. So let's say the network is Roger. So HLR would contain information of Roger's subscribers. VLR is for visitor from outside the network. So let's say someone from Thales who roams into the system, the Rogers network, then the VLR would contain that information, right? The database, the visitor location register here, okay? And then we have something here we call AUC, which is Authentication Center, okay? Authentication Center. And then we have another component called EIR, Equipment Identity Register. Okay, so this is to make sure that the equipment used in the phone, used in the network are valid phones. Okay, so with these and the switching center control on these, it will make sure that the network is managed properly. Okay, all right. So one thing that this part provides is to connect the mobile network to the landline network, okay, to the other networks here. Okay, it's provided to other networks here, to the landline networks. The second function of this is to provide subscriber management functions, such as mobile registration, location updates, authentication, and call routing for roaming subscriber. All right. So mobile registration is for the home user, for example, location updates, and then authentication is done by EIR and the authentication center. And the call routing for roaming subscriber can be done using the VLR. Okay. All right. Okay. So let's, I think we can finish this part, and then we say part 2 for the second, for the second lecture. So we finish this switch first. All right. It's okay. I think we can stop here because I think it's the end of the lecture and the rest is a lot of detail. So we can stop here at the general architecture. And then in the next lecture, we'll go into details of each component of these, because I think that would be too much for the end of this lecture here. All right. Okay. So again, for the next quiz, it'll be everything from multi-rate transmission up to this diagram here. Okay. So we only need to, you only need to go to this diagram, the 4 subsystem and this diagram, and then we save the rest after this for the next lecture. All right. Okay. So the quiz, just like in the past, 5 to 7 questions, multiple choice questions, and that's it. Okay. 5 to 7 multiple choice questions. All right. So I will stay for the next 5 to 10 minutes if you have questions to ask. All right. Okay. Otherwise, I'll see you next week. And tomorrow I have office hour from 12 p.m. to 12:45 p.m. All right. So thank you everyone for participating in the lecture. And I'll see you either tomorrow in the office hour or next week in the lecture. Okay. So Joshua has a question. Will you be extending today assignment right after the lecture? Yes, I will be extending right after the lecture. So I'm doing it right now. And you can check to see if you get the extension or not. 1 second. I'll do this right now. Okay, 1 second. And if you have questions, feel free to ask. Okay. I'll be here for the next 5 and 10 minutes. So have a nice evening, everyone, and have a nice weekend. Yes, Samia. Yes, you can talk about your midterm tomorrow in the office hours. Yes. Okay, so yeah, tomorrow at 12 p.m. You can ask about the midterm, right? So let me Joshua has a question. Are midterm available for pickup next week every day? I'm not sure about every day because I'm in only on Tuesday. So, and I'm not sure if I leave the midterm outside my office or the custodian may remove them. Yeah, so let me think how I will think about a way to leave the midterm paper somewhere, all right? Upload, sorry, I cannot upload them online. I don't have a scanner. And it would take a very long time to scan all the paper. All right. So Joshua, can you check to see if you can access the homework? Yeah, I cannot upload your paper online because I don't have a scanner. And even if I had a scanner, it would take a long, long time to scan all the papers. Yeah. You're welcome, Joshua. Yeah. Okay. So Samyak, you can attend the office hour tomorrow, and then I can show you the solution, right? Yeah, so I will leave the paper somewhere so you can pick them up anytime. I will try to find a way, and I'll send a message, an announcement, and then to let everyone know. So what I'm thinking is to leave the papers with the lab monitors in the Prism lab, you know, on the first floor of the lab, Prism lab. There are always monitors there. So I think probably I'll leave that with those TAs. So I will check with them and I'll let you know. Yeah. All right. So I'll check with them to make sure that they agree to that as well. Then I'll let you know. Yeah. Okay. Yeah, that's what I'm thinking. That's the best solution. Yeah. Okay, so I don't see any more questions. All right, so yeah, so I will find a way to leave the test papers with someone in Lason building, and then I'll send a message to everyone. All right. Okay, so have a nice evening and have a nice weekend, everyone. And I'll see you next week. Okay, bye for now. Yeah, thank you, Paul. See you next week.